This section explains why logic and proofs form the foundation the rest of the book stands on. Truth becomes mechanical once you separate a statement's form from its content. Logic supplies the grammar, the connectives, and quantifiers that compose atomic propositions into structures whose truth value is forced by the parts, computable without knowing what the parts mean. A proof is then nothing but a path whose every step is a truth-preserving rule. Start from what holds, apply inferences that cannot manufacture falsehood, and arrive somewhere new that must also hold. This is the chapter that earns the rest of the book. Every later object, the sets and functions and induction arguments, is asserted and justified in exactly this currency. Master the move once, and every subsequent claim in discrete mathematics is the same move, re-instantiated. This section explains what a proposition is and the single move that lets logic mechanize it. A proposition is a declarative sentence carrying exactly one truth value, true or false, the smallest unit logic can grip. Everything the chapter then does follows from a single move. The connectives, not, and, or, the conditional, and the biconditional, are truth functions. Each connective takes only the truth values of its parts and returns a truth value. So a compound's truth is fixed entirely by the truths of its atoms. The sentence's actual meaning does not survive the abstraction. The conditional has one counterintuitive line. It is false solely when a true hypothesis yields a false conclusion. That line is simply what its truth table says, a stipulation to read off rather than a fact to intuit. This is the substrate the rest of the book stands on. Collapse assertion to truth value, make composition purely functional, and proof becomes mechanizable later. This section explains how propositional logic gets applied. The whole section runs on one move. You bind each atomic English claim to a propositional variable, and the sentence's logical skeleton, its and, its or, its not, its if, then, becomes a formula a machine can manipulate. Once translated, meaning stops being negotiable. The question, is this system specification consistent, collapses to the question, is this conjunction satisfiable? A search query, a logic puzzle, a circuit's output are the same question wearing different clothes. The applications differ only in what the atoms denote, sensor states, search terms, wires. They never differ in the mechanics. That is the surprise. Propositional logic contributes no cleverness of its own. It is a notation that makes the cleverness already latent in the words computable. Ambiguity is what translation costs you at the door. This section explains what it means for two logical formulas to be the same. Two formulas are the same when they compute the same truth function, when they agree in every row of the truth table, regardless of how differently they are written. That single move, identifying a proposition with what it does to truth values rather than the symbols it is built from, is the whole section. Logical equivalence, written P is logically equivalent to Q, is itself a definition. P if and only if Q is a tautology. Once meaning collapses onto the truth function, the named laws, De Morgan, distributivity, absorption, are the algebra on that quotient, and you may transform a formula by substituting equals for equals. Instead of re-quotient, you may transform a formula by substituting equals for equals instead of recomputing it. Syntax becomes rewritable because semantics has been made the invariant. The equivalences are that invariants tabulated. This section explains how predicates and quantifiers let logic reach inside a sentence instead of only combining sentences whole. A proposition is opaque. Socrates is mortal has no moving parts. A predicate cracks it open. P of X is a proposition with a whole, a function from a domain into truth. Values, meaningless until the whole is filled. Quantifiers fill the whole without naming a value. For all x, P of x renders one verdict over the entire domain. There exists x, P of x renders another. Here's the compression. Quantifiers are infinitary Boolean connectives over a finite domain, for all is literally the conjunction P of a 1 and P of a 2 and so on up to P of n. There exists is the matching disjunction. Extend this to infinite domains and you have something propositional logic could never say. That is the whole leap of the section. You move from sentences you can only combine to sentences you can reach inside and range over. This section explains how the order of nested quantifiers determines a statement's meaning. Order is the whole content. A quantifier prefix reads left to right as a dependency chain. Each variable is bound after those to its left, so it may depend on them. Take for all x, there exists y, such that P holds of x and y. This says every x gets its own y, chosen with x already known. Now reverse it, there exists y, such that for all x, P holds of x and y. This demands one y serving all x at once. The nesting places. The existential y inside the scope of the universal x, and that containment is exactly the license for y to be a function of x. Swapping two like quantifiers is free. Swapping unlike ones, a for all past A, there exists, generally changes the proposition. The smallest transfer, think of the prefix as who chooses in what order. Later choosers see earlier moves. This section explains why the validity of an argument is a matter of form alone. Validity lives in form. The content of the propositions never enters the judgment, and that is the whole move. An argument is valid when the conditional premises, therefore conclusion, is a tautology. Whether the premises are actually true is a separate question the logic never touches. So truth becomes a fluid that the argument only transports. Feed true premises into a valid form and a true conclusion drops out. It does so blindly, without ever reading what the propositions mean. Modus ponens is the atomic transporter from P, and P implies Q. Infer Q. Every rule is a small tautology in disguise, and a proof is just these atoms chained together so that truth flows from premise to conclusion mechanically. This meaning, free transport is precisely what makes the whole process automatable. This section explains why every proof method exists and what single case each one closes off. A theorem is a conditional. If P, then Q. It is false in exactly one situation, P true, while Q false. Every proof method is a route that closes off that single situation, and the menu comes from the conditional's own logical equivalences. A direct proof enters at P and forces Q. Proof, by contraposition, attacks the identical case from the far side, deriving not P from not Q. Proof by contradiction supposes the forbidden case, holds and extracts an absurdity. Vacuous and trivial proofs dispatch the degenerate cases where it cannot arise at all. The section's real turn is from checking truth, the earlier truth tables, to establishing it. One object, now made generative. This section explains why proof strategy is a separate skill from the proof techniques that came before it. Every prior section handed you a proof technique. This one confesses that none of them tells you which to reach for. Proof finding is search rather than execution, a space of statements lying between hypothesis and goal, crossed by heuristics, never by algorithm. The governing move is meeting in the middle. Forward reasoning grows consequences from what is given. Backward reasoning asks, what would suffice for the goal? You strategize until the two fronts touch. A universal claim dies to one counterexample. An existential lags on one construction. That asymmetry dictates where to spend effort. The boundary is what shows the structure. Some conjectures, and here Rosen closes the chapter on open problems, admit no strategy at all, search with no guarantee of halting. This section explains the single move that everything discrete mathematics builds later rests on. An object is fixed entirely by what belongs to it. A set is nothing but its membership predicate. Extensionality means two sets with the same elements are the same set, so the container has no identity beyond its contents. A function is then a set of ordered pairs, constrained so that each input pairs with exactly one output. The words rule, formula, and algorithm are just ways of naming that graph. This is the whole content of the chapter. The sequences, sums, matrices, and relations that follow are each a set carrying a function on it. Fix membership, fix the single valuedness constraint, and every downstream structure is already determined by composition, with nothing new added. This section explains what a set is at its most reduced. A set is fixed entirely by one question, asked of every object. Are you in? Nothing else survives. No order, no repetition, no internal structure. This is extensionality. Two collections with the same members are the same set, full stop. The identity of the whole reduces to its membership predicate. So the collection 1, 2, the collection 2, 1, and the collection 1, 1, 2 are all one object because they answer the in question identically for every candidate. The generative move is that a set is its characteristic function, a map from the universe to yes or no. The collection and the predicate are two views of one thing. Everything downstream, union, subset, power set, is just algebra on that yes or no answer. The container has no memory beyond who it holds. This section explains why every set operation is a logical connective wearing a membership predicate, union is or, intersection is and, complement is not, difference is and not. This holds because X is a member of A, union B means exactly X is a member of A or X is a member of B. Where the previous section handed you sets, this section puts algebra on them. And that algebra is a single isomorphism. The Boolean algebra of propositions maps onto the algebra of sets, with membership carrying truth across. So, De Morgan, distributivity, and idempotence are not fresh laws to memorize. They are Chapter 1's propositional identities, read through the membership relation. Prove any set identity by proving its logical twin. A Venn diagram is just this correspondence drawn, where each region is one row of a truth table. This section explains what a function is and why its named properties matter. A function is the formal shape of exactly one output per input, determinism made into an object. Give it a domain, and it stamps each element with a single name in the codomain. Nothing in the domain goes unnamed, and nothing gets two names. That single constraint is the entire content, and everything Rosen builds on it is a diagnosis of the stamping. Injective asks whether distinct inputs ever collide. Surjective asks whether every codomain element gets used. Bijective is both at once the exact condition under which the stamping runs backwards into an inverse. Read this way. A function is just a relation disciplined into single valuedness, and its named properties are the precise obstructions to undoing it. This section explains why sequences and summations are a single primitive already met, the function seen from a new angle. A sequence is a function whose domain has been renamed. Feed it the natural numbers, collect the outputs in a set, and function application becomes indexing. The term written A sub n is just A of n. A summation is that same object folded. The summation operator accumulates the function's outputs over a chosen slice of its domain. So this section imports a single primitive from the one before it, the function, now restricted to a discrete, ordered index. The closed forms, geometric and arithmetic, are not luck. They surface precisely when the term function carries enough structure that the fold telescopes. From this, you can predict the rest. Any indexed object is a function, and any sum is a fold over 1. This section explains how the chapter measures the size of infinite sets. Counting stops working at infinity, so the chapter replaces it with something that does not break. Two sets have the same size when a bijection matches their elements, 1 to 1, with no remainder. That single move, treating size as the existence of a matching map rather than a tally, is the whole section, and it survives the jump past the finite. The payoff is immediate and strange. The integers, the rationals, and the pairs all admit such a matching with the positive integers. Each is countable, with cardinality aleph null. Yet the reals do not admit such a matching. Cantor's diagonal argument forces a mismatch that no listing can repair. So the word infinite fractures into a hierarchy. Countable versus uncountable is its first cut. An equinumerosity by bijection is the blade that makes the cut visible. This section explains why a matrix has the multiplication rule it has. A matrix earns its multiplication rule, and the rule is composition. Row I times column j, summing the products over every intermediate index k is exactly this. Root through all the middle states and total the throughput. So the rectangular array is only bookkeeping for a linear map, and the product of two arrays is the composite map. Rosen's 0-1 case strips this to the skeleton. Swap sum and product for or, and matrix multiplication becomes relation composition. The entry asks whether some middle index k gives both a step from I to k and a step from k to j. In other words, is there a two-step path? Everything else in section 2.6 reads off this one identity. Powers count paths of length n. The transpose reverses direction. And symmetry means direction is ignored. This section explains what an algorithm is and why that definition already fixes how we measure its speed. An algorithm is a procedure specified finitely enough to run, yet abstractly enough to survive any machine or any language. It is what the procedure does to its input, never how it is coded. That single act of decoupling is the whole chapter. Once the procedure floats free of its implementation, the only invariant left to grade it by must also float free of hardware, and that invariant is growth rate. Big O is the equivalence, relation doing the floating. It quotients away constants and clock speed, keeping only how cost scales with input size. So what does this algorithm and how fast is it turn out to be one question, answered by the same abstraction. This section explains what an algorithm actually is, at the level of definition rather than code. An algorithm is defined by what it must satisfy, never by the syntax expressing it. Rosen opens with the finding, the maximum procedure, and immediately abstracts away from it. The properties are the definition, input, output, definiteness, correctness, finiteness, effectiveness, and generality. This is the universal property move applied to computation, The object is what it does. So max finding, linear search, and binary search all become one kind of thing, seen through one specification lens. The chapter's role in the book's arc is to install exactly this, a machine-independent notion of procedure. It is made precise enough that later chapters can measure it, rather than merely run it. This section explains growth order, the property that survives once you stop caring about constant factors and small inputs. Declare f dominated by g when, past some threshold, f of x never exceeds c times g of x for a single fixed c. That is big O, a pre-order ranking functions by eventual shape alone. Two witnesses, C and K, certify the claim. Everything below K and every multiplicative constant is quotiented away, so 3x squared plus 50x plus 7 and x squared collapse into one class. Big theta is mutual domination, the equivalents whose classes are the true growth rates, the generative move to compare algorithms, coarse-grain, their cost functions until only the dominant term still speaks. This section explains how the cost of an algorithm is measured and why that measure reduces to a single feature. An algorithm's cost is a function, operations counted against input size n, and the only feature that survives to matter is its growth class. That is the whole move. Collapse the exact operation count to its dominant term, read off big O of n squared, big O of log n, big O of log n, big O of 1, and compare algorithms by how their curves diverge as n grows, never by their behavior on any single input. The worked exercises are all one gesture from different angles. Nested loops multiply their bounds. A doubling counter terminates in log n steps. Repeated squaring beats naive powers. Section 3.2's big O machinery becomes, here, a ruler laid against running time. Sane answer algorithms are not equal. The exponent decides. This section explains why the arithmetic of number theory becomes the foundation of cryptography. Divisibility is the only relation on the integers that survives. Collapse into a finite world. Fix a modulus n. Quotient the integers into residue classes, and addition and multiplication descend cleanly onto the finite set, arithmetic modulo n. The chapter's single thread is that this finite arithmetic is computationally lopsided. Forward operations, multiply two primes, exponentiate a residue, are cheap. Their inverses, factor the product, take a discrete logarithm, have no known chief root. Everything before. Section 4.6, the greatest common divisor, the Euclidean algorithm, primes, solving congruences, is the machinery that makes the forward direction fast and certifies the backward direction hard. Cryptography is what you build once you own a lock that only opens one way. This section explains congruence modulo and why arithmetic survives it. Two integers count as the same. The instant m divides their difference. That single relation, congruence mod m, folds the infinite integer line into m residue classes. The fact that makes everything downstream work is compatibility. If A is congruent to B and C is congruent to D, then A plus C is congruent to B plus D, and A times C is congruent to B times D. Addition and multiplication survive the fold, so arithmetic descends onto the finite quotient, the integers mod m, intact. Divisibility is the degenerate case, the one where the remainder is zero. The division algorithm, Writing a as q times m plus r with r at least 0 and less than m guarantees that every integer lands in exactly one class. This is the section the rest of Chapter 4 stands on. Primes, greatest common divisor, congruence, solving, and RSA are all just arithmetic performed inside such a structure-preserving quotient. This section explains how integers are represented and why the choice of representation shapes every algorithm that acts on them. An integer is basis-free. Its base b. Expansion is a coordinate choice, the same value written as digit operations. P. Every algorithm here lives in that coordinate, never in the number itself. Addition, multiplication, and division all become position, local digit manipulation with carry propagation. And cost is counted in digit operations. Fix the pattern once, and each base follows. Change b, and only the digit alphabet moves, while the procedure stays fixed. The real yield is fast, modular exponentiation. Reading the exponent's own binary digits turns b to the n into square and multiply, collapsing n multiplications down to the logarithm of n. Choosing a representation is choosing which operations you have made cheap. This section explains how prime numbers give multiplication its basis, and how that one idea sets the whole multiplicative order of the integers. Multiplication has a basis. The primes are the atoms, no smaller product reaches, and the fundamental theorem of arithmetic says every integer is one unique product of them. Factorization is a coordinate system, each integer a vector of prime exponents. Once you see that, the rest collapses. The greatest common divisor is the component-wise minimum of those exponents. The least common multiple is the maximum. Divisibility is just less than or equal to in every coordinate. The section's quiet surprise is that you never need the coordinates to find the greatest common divisor. Euclid's repeated remainder extracts it from the raw pair, factoring free. Primes as basis, the greatest common divisor as meat in the divisibility lattice, the whole multiplicative order of the integers, read off one structure. This section explains how to solve a linear congruence, and why every method in it reduces to just two ideas. A congruence, written ax, is congruent to b modulo m, is a division problem inside a finite ring. You recover x by multiplying through by the inverse of a. That inverse exists exactly when a is a unit, which means the greatest common divisor of a and m equals 1, and the extended Euclidean algorithm constructs it. So deciding whether a solution exists and actually solving esolve, preminent, each, where solve, and ext. The move that carries the section is the Chinese remainder theorem. For coprime moduli, residues become independent coordinates. The ring of integers modulo m times n is isomorphic to the product of the ring modulo m and the ring modulo n. A number is exactly its tuple of remainders, and a system of congruences simply names one point, coordinate by coordinate. Every technique in the section is either inverting a unit or reading that factorization. Predict the rest from those two. This section explains what all the applications of congruences share. Reduce an integer modulo m, and the infinite line of integers collapses onto a finite wheel of m residues. Every application here is a choice of what you want that collapse to preserve. Hashing wants collisions rare, so it spreads keys evenly across the wheel. The linear congruential generator wants the orbit that sends x to a times x plus c, modulo m, to visit every residue before it repeats. a long period bought from a single multiplication. Check digits want the common slips, a wrong digit or 2 digits transposed, to shift a 1 digit or 2 digits transposed, to shift a weighted residue, so the checksum betrays the error. One projection from the integers to the integers modulo m read through 3 desiderata. The modulus and the weights are the entire design. Choose m carelessly and each guarantee dissolves. This section explains how number theory turns into a lock. Every classical cipher here, Caesar's shift in the affine map, is just a bijection on the integers modulo n. Encryption permutes the residues. Decryption applies the inverse permutation. A permutation that anyone can invert is only obfuscation. The whole arc of the section bends toward the one move that breaks that symmetry, RSA. There, the same modular exponentiation is cheap in the forward direction and infeasible in reverse, unless you hold the factorization of n. That asymmetry is the primitive, a bijection whose inverse is gated on a hard problem. Read this way. All of Chapter 4, divisibility, primes, congruences, Fermat, was scaffolding erected to make one-way functions exist. This section shows how induction and recursion are one structural move seen twice. The natural numbers carry a well-ordering. Every non-empty subset has a least element. That single fact licenses two mirrored operations. You may define an object by giving a base case and a rule that reaches n from its predecessors, which is recursion. And you may prove a property the same way base plus, inductive step, which is recursion. Building and verifying share one skeleton. The step that constructs f of n plus 1 from f of n is the step that carries the truth forward. Rosen threads all 5 sections through this identity: ordinary induction, strong induction, structural definitions, recursive algorithms, and program correctness. Learn the base and step reflex once. Every instance is the same clepsydra dripping forward from a fixed source. This section explains mathematical induction as a way to prove an infinite claim with only 2 finite acts. An infinite claim collapses to 2 finite acts because the natural numbers have no gaps. Every one of them is reached from the base by finitely, many plus 1 steps. So to prove P of n for all n, you never inspect infinitely many cases. Instead, you show that truth transports across the successor, that P of k implies P of k plus 1, and then you light the base P of k plus 1, and then you light the base. Rosen's ladder makes it visceral. Reach the bottom rung, guarantee that each rung lifts you to the next, and every rung is yours. The generative move is this. Induction is recursion. Run in proof space, the successor structure of the natural numbers turned into an engine. Wherever a structure is built by one repeated step from a seed, this same shape proves things about all of it. This section shows that 3 statements about the natural numbers are secretly one statement. The first is ordinary induction. If p holds at n, then p holds at n plus 1. The second is strong induction. If p holds on the entire prefix, every value less than or equal to n, then p holds at n plus 1. The third is the well-ordering property. Every non-empty set of non-negative integers has a least element. Proving these 3 equivalent is the whole section. The generative move is this. A proof by induction is the contrapositive of well-ordering. You assume there is a set of counterexamples. Well-ordering hands you a least one, and the inductive step shows that this least element cannot actually be least. So the counterexample set is empty. Strong induction only widens the hypothesis from a single predecessor to all of them. That wider assumption is free to take, and it becomes necessary exactly when p at n plus 1 leans on several earlier cases at once, as in prime factorization or Fibonacci-style recurrences. This section explains how a set built from constructors carries proof by structural induction. A set defined by its constructors is just the closure of a basis under a handful of building rules, the smallest set that contains the seeds and stays shut under the operations. Once an object is its construction, proving a property over all such objects needs no integer to count up. You show it holds for the seeds, then that every rule preserves it. That is structural induction. Induction run along the construction tree instead of along the natural numbers. The two are one move. Ordinary induction is the special case where the single constructor is the map that sends n to n plus 1 and the tree degenerates to a line. Match the proof shape to the definition's shape, and the property propagates outward exactly as the elements were built. This section explains recursive algorithms as inductive proofs run forward. A recursive algorithm is an inductive proof run forward. You define the procedure on an input by invoking itself on strictly smaller inputs, terminating at a base case. You can answer outright. The same well-ordering of the naturals that licenses induction, the fact that every descending chain bottoms out, is exactly what guarantees the recursion halts. The algorithm and its correctness proof are the same object, read in two directions. Consider three cases. Factorial calls factorial of n-1. Euclid reduces the greatest common divisor of a and b to the greatest common divisor of b and a modulo b. Merge. Sort halves its list. Each one names a base case and a shrink toward it, nothing more. You can predict the shape anywhere. With no strictly smaller subproblem, there is no recursion. With no reachable base, there is no termination. This section explains why a correct program is really a theorem in disguise. A program becomes a theorem, given that the initial assertion holds before execution, the final assertion holds after. This is partial correctness, correctness granted the separate promise that the program halts. The proof composes step by step. Every construct falls to this, except the one that matters, the loop, whose iteration count you do not know. That single obstruction is dissolved by the loop invariant, a proposition true before entry and preserved by one pass, so induction carries it across arbitrarily many. It is a conserved quantity, turning an unbounded process into a finite argument. The same move as any proof by induction, now aimed at code. Testing exhibits a bug where one exists. This exhibits its absence. This section explains what counting is at its structural root. Counting is refusing to enumerate. A finite set size is read off the recipe that builds it, never off the elements themselves. Choices chained by and multiply. Alternatives joined by or add. Symmetries you declared irrelevant divide back out. That one homomorphism from construction to arithmetic generates the whole chapter. Permutations are the bare product rule. Combinations are the same product, quotiented by the orderings you refuse to distinguish. Binomial coefficients are that quotient given a name. The pigeonhole principle is the dual gesture. When the built set outsizes the labels available, collision is forced, existence wrung from a cardinality mismatch, still without listing a single object. This section explains the basics of counting. Counting a set means finding the size of a task's choice, structure, and every such structure decomposes two ways. Sequential, independent stages multiply. This is the product rule, and it counts a Cartesian product. The size of the set of pairs drawn from A and B equals the size of A times the size of B. Mutually exclusive alternatives add. This is the sum rule, and it counts a disjoint union. That is the entire engine. Read any counting problem as a tree of and, then nodes which multiply and or nodes which add, and the count falls out of its shape. Overlap between cases violates the disjointness the sum rule assumes. Correcting for that overlap is the next mechanism the chapter builds. The quiet elegance is that arithmetic's two operations are the two ways finite structure composes, the product and the coproduct of finite sets. This section explains the pigeonhole principle. Push more pigeons than holes, and some whole holes, too. That is the whole of it, and its power hides in how little it says. The principle is just non-injectivity made visible. No function from a larger finite set into a smaller. One can stay. 1 to 1, so a collision is forced. What makes it a primitive rather than a triviality is the shape of conclusion it buys. Pure existence, purchased by counting alone. You learn that two people share a birthday count, that some pair sits at equal distance without ever naming which. Contrast a constructive proof which must exhibit its witness. Pigeonhole guarantees the witness exists while refusing to point at it. Order is the only variable, and dividing it out is the whole of this section. Selecting R things from N is an injection into R labeled slots. That count is P of N, R, which equals N factorial divided by the factorial of N minus R. And it is ordered. A combination is the same selection with the slot labels forgotten. C of N, R equals P of N, R divided by R factorial. That R factorial is no accident of arithmetic. It is the size of S sub R, the group permuting the orderings you refuse to distinguish. So a combination is a permutation quotiented by the symmetry of order. Every later counting identity, the binomial coefficients, Pascal's recurrence, inherits this one move. Count the ordered version where it is easy, then divide by the size of the symmetry you are ignoring. This section explains why one number, the binomial coefficient, carries two meanings at once, and how a single counting move generates every identity around it. One number wears two faces. The binomial coefficient n, choose k, counts the k element subsets of an n element set, and it also weights the x to the k term in the expansion of x plus y, all to the n. The binomial theorem is the hinge between them. Expanding that product means choosing x from k of the n factors, so the counting is the k efficient in think of the n factors, so the counting is the coefficient. Every identity in the section then falls out of one move. Name a set, count it two ways, and equate the results. Pascal's identity splits the subsets by whether they hold the last element. The row sum, 2 to the n, counts all subsets at once against counting them size by size. Vandermon's identity partitions a choice across two urns. Learn the move, double counting, and you generate the identities rather than memorize them. The algebra is just the combinatorics read aloud. This section explains how the four counting formulas of section 6.5 collapse into a single idea. Drop two silent assumptions of the earlier counting rules, that objects are all distinct and that none is reused, and all four formulas reduce to one schema, placing R balls into N boxes. Whether the balls are distinguishable and whether a box caps at one forms a 2x2 grid, and that grid is the section itself. The step that does the work is stars and bars. Choosing R items from N with repetition equals choosing where to drop N-1 dividers among R stars, which gives the combination of N plus R-1. Choose R. Ordered with repetition gives N to the power R. Indistinguishable copies give the multinomial n factorial divided by the product of n1 factorial through nk factorial. One picture distribution generates all four, so you can now predict the case the section does not name. This section explains how to generate permutations and combinations one at a time. Counting tells you how many. This hands you each one exactly once. The move is to impose a total order, lexicographic, on all permutations or on all R combinations of a set. That turns the collection into a line. Then you define a successor function that walks from the current arrangement to the next without ever holding the whole set at once. For permutations, the successor is local surgery. Find the rightmost ascent. Swap that entry against the smallest larger element to its right. Then reverse the tail. The tail was descending the last arrangement of its block, so reversing it yields the first of the next block. Enumeration collapses to iterated succession over a well-ordering. Storage falls from exponential to a single array you keep overriding. This section explains how discrete probability begins as counting and slowly sheds every assumption until only the structure is left. Probability enters as counting made into a ratio. Laplace is favorable over total, and the whole arc of the chapter is watching that ratio drop its assumptions until only the structure remains. First, the outcomes must be equally likely. Then, section 7.2 lifts the definition to any normalized weight on the sample space. So probability becomes a measure and counting was merely its uniform special case. Conditioning reweights that measure by evidence. Bayes inverts the conditioning. Expectation collapses the weighted outcomes back to a single number. Here is the surprise. The chapter understates. Expectation is linear no matter what. Sums of dependent variables still add, because linearity lives in the weighting, not in independence. Counting was never the point. The normalized measure was the point all along. This section introduces discrete probability. Probability, at its first cut, is counting wearing a normalization. Laplace's definition sets the probability of an event. E equal to the size of E divided by the size of S, the favorable outcomes divided by the total, when every outcome is equally likely. That single equation is what this chapter is for in the book's arc. It converts the combinatorics you already built into a measure. Every question here, a poker hand, a lottery, the birthday coincidence, resolves into two counting problems, stacked in a ratio. Nothing new is asked of you but division. The assumption. The rest depends on hides in the words equally likely. The moment outcomes carry unequal weight, the ratio breaks, and the next section must replace counting with a weighted sum. This section explains how probability, at its foundation, is just counting made proportional. Probability here is counting, normalized. Laplace's rule says that the probability of an event equals the number of outcomes in that event divided by the number of outcomes in the whole sample space. When outcomes are equally likely, the chance of an event is the fraction of the sample space it fills. So every probability question dissolves into two combinatorial questions from the previous chapter. The chapter's real move is the quiet generalization. Past that, replace equally likely with an arbitrary weight function, one that assigns each outcome a non-negative number, with all the numbers summing to 1. Then the probability of an event becomes the sum of the weights inside that event. Laplace is the uniform special case. That is the whole primitive. A probability is a unit of mass spread over possibilities, and combinatorics tells you how much sits where. This section explains Bayes' theorem as a single move, reversing an arrow of dependence. You are handed the probability of the evidence given the hypothesis, how likely the evidence is if the hypothesis holds. What you want is the reverse, the probability of the hypothesis given the evidence, how likely the hypothesis is given what you actually saw. Bayes' theorem is the exact exchange rate between these two directions. Its only moving parts are the prior, the probability of the hypothesis on its own, and the same computation run against the negation of that hypothesis on the evidence. The chapter's spam and disease examples exist to stage 1 surprise. A test that is right 9 times in 10 still leaves you mostly wrong when the hypothesis is rare, because the prior outweighs the test's accuracy. Belief is evidence reweighted by the base rate, never evidence alone. This section explains expectation and variance as the two numbers you extract from a random variable and the single linear operation that gives you both. Expectation is a linear functional. It sends a random variable to the probability weighted average of its values, and the expected value of x plus y equals the expected value of x plus the expected value of y, whether or not x and y interact. That single fact is the section's lever. A hard count, the expected number of fixed points of a random permutation, or the expected number of comparisons in a sort, dissolves once you write the quantity as a sum of indicator variables and add their easy expectations one by one. Variance is the complementary primitive, the expected value of the square of x minus its own expectation, the weighted spread. Its shortcut, the expected value of x squared minus the square of the expected value, together with multiplicativity under independence, let Chebyshev bound how far a variable strays. Two numbers, center and spread, extracted by one linear operation and its second moment. This section explains the single move behind advanced counting. When a set resists the direct rules of Chapter 6, product, sum, permutation, combination, you stop counting its elements and start counting the structure that generates them. That is the single move this chapter teaches. A recurrence counts by how the collection grows from smaller copies of itself. A generating function hides the whole sequence inside one power series and lets algebra extract the coefficient. Inclusion and exclusion counts sloppily on purpose, then subtracts the overlaps back out. These are 3 faces of one idea. Each transforms an intractable enumeration into a solvable relation, recursive, algebraic, or corrective, and then you read the answer off the solution. Count the process, not the objects. This section explains why counting problems dissolve into recurrence relations and what the recurrence really is. Count anything by finding where the object of size n hides a smaller copy of itself. That is the whole move. A recurrence is a decomposition. You locate the single choice or step that peels an instance down to size n-1, or splits it into k and n minus k, and the count at that boundary combines with the subcount. Take the Tower of Hanoi, move the top n-1 disks aside, shift 1 disk, move them back. The count for n disks equals twice the count for n-1 disks plus 1, and that falls straight out of the physical act. The breeding rabbits give Fibonacci by the same reflex. Dynamic programming is this reflex weaponized. Modeling is the answer here. Solving the recurrence waits for later. This section explains how to solve a linear recurrence relation with constant coefficients. Guess that the sequence grows like a pure geometric mode so that a sub n equals r to the power n. A linear recurrence with constant coefficients then collapses. Every term becomes r to the n times a power of r. The common factor divides out, and what remains is a single polynomial in r, the characteristic equation. Its roots are the sequence's natural growth rates. The general solution is their weighted superposition, and the initial conditions fix the weights. That is the whole engine. It is the same eigenvalue move that diagonalizes a linear ODE, and a recurrence is just its discrete shadow, with the shift operator standing where the derivative stood. A repeated root is the one wrinkle. It forces a second mode, n times r to the n, exactly as degeneracy does elsewhere. This section explains how divide and conquer algorithms get their running time from a single accounting rule. A recursive split obeys one accounting identity. Solving a problem of size n costs a subproblems of size n over b, plus the merge work g of n. The entire cost tree is then governed by a single race. Does the branching factor outrun how fast the per-level work shrinks? Compare A against B raised to the degree of the merge. Either the subproblems dominate, or the merge dominates, or the two tie. Those three regimes are the whole master theorem. You never unroll the recursion. You read off which end of the tree carries the cost. An algorithm's speed becomes a verdict of leaf count versus root cost, settled before any code runs. Binary search, merge sort, and fast multiplication all fall out of where it lands. This section explains generating functions. A generating function buries an entire sequence, a 0, a 1, a 2, and so on, inside one object. That object is a formal power series, and the value a sub n is simply the coefficient of x to the n. Wilf called it a clothesline, the numbers hung on powers of x for display. The payoff is that algebra on the function mirrors operations on the sequence. Multiplying two generating functions convolves their coefficients, so the task of choosing parts that sum to n collapses into a single product, and a recurrence becomes one equation you solve in closed form. You then read the answer back off the coefficient. Here is the structural boundary. The variable x is pure bookkeeping, never evaluated, so convergence is irrelevant. The object is formal, its algebra symbolic rather than analytic. Counting becomes coefficient. This section explains inclusion and exclusion, the correction that makes counting a union come out right. Counting a union goes wrong the instant its parts overlap. Add the sizes, and every shared element is tallied twice. Inclusion and exclusion is the correction. Add the singles, subtract the pairwise overlaps, add back the triples, alternating signs all the way down to the full intersection. The generative pattern is cancellation bookkeeping. An element lying in exactly k of the sets gets counted. K, choose 1, minus k, choose 2, plus k, choose 3, and so on. That alternating binomial sum collapses to exactly 1. So every element is counted once, no matter how deep its overlap. Given that, you can predict the whole family. Surjections, derangements, Euler's totient, each is the same alternating sweep over a different bad property to exclude. This section shows how one counting move wears many different costumes across every application. The move is this: to count objects having none of a listed set of properties, do not attack the negation directly. Take the whole universe and subtract the alternating sum of how many objects satisfy each combination of properties. Watch the same move under 4 disguises. Onto functions become the condition of missing no element of the codomain. Derangements become the condition of fixing no point. the sieve becomes divisible by no small prime. Euler's phi is the same computation carried out over the prime factors. Choosing which properties to name is the entire art. The alternating machine underneath never changes. Here is the structural surprise. The section hands you derangements. Taken as a fraction of all permutations, converge to 1 over e. The chance that nothing lands in place is nearly constant, indifferent to n. This section explains what a relation is at its most primitive, and how two familiar structures fall out of it. A relation is nothing but a subset of a Cartesian product. You pick which pairs of A cross B you keep, and that choice is the relation. Everything comparative collapses into this one object: equality, the divides relation, less than, graph edges, database rows, congruence. The surprise the chapter threads is that the same four properties, reflexive, symmetric, antisymmetric, and transitive, recombine into exactly two great attractors. Keep reflexive, symmetric, and transitive together, and you get equivalence. Equivalence is sameness, and it shatters a set into disjoint classes. Swap symmetry for antisymmetry, and you get partial order. Partial order is hierarchy, and it stacks a set into levels. One primitive, a chosen set of pairs, and comparison, partition, and ranking all fall out as which axioms you switch on. This section explains what a relation is and why its four named properties are all the same kind of thing. A relation is just a subset of a cross B. The entire content of the notion is which ordered pairs you keep. Everything else here is one constraint shape. If certain pairs are present, certain others must be too. Reflexivity demands every diagonal pair paired with A. Symmetry demands the pair BA whenever you have the pair AB. Transitivity demands the pair AC whenever the pairs AB and BC chain together. Antisymmetry forbids the pair BA once the pair AB holds, unless A equals B. Read as quantified implications over the set of pairs, the four properties stop being a list. They are closure or exclusion conditions on a set of pairs, and composition is nothing but chaining the implications you already hold. Predict the next property by asking what it forces present or absent. This section explains the single identification behind every database. A table is a subset of a Cartesian product. That is the whole chapter. Extend the binary relation from pairs to n, tuples. A relation on A, 1 through AN, is any subset of the Cartesian product. A1 crossed through AN, and a database record is one such tuple, its columns, the factor sets AI. Everything, database, shaped falls out of this single identification. A primary key is a coordinate on which the projection stays injective. One field value pins the whole tuple. Querying is set operation. Selecting rows filters the subset. Projecting drops coordinates, joining glues two relations along a shared domain. This is Codd's relational model. Reduced data is a relation, and asking questions of it is manipulating subsets of a product. This section explains how to represent a relation on a finite set so that its properties become visible. A relation on a finite set is a table of yes and no answers, so store it as exactly that. The 0-1 matrix whose entry in row I and can see is 1 precisely when a sub I is related to a sub j. The same object can be drawn instead as a directed graph, carrying an arrow from I to j under that same condition. These are two coordinate systems on one thing, and every abstract property collapses on one thing, and every abstract property collapses into a pattern you can see. Reflexive means an all-ones diagonal, a loop at every vertex. Symmetric means the matrix equals its transpose, every arrow paired with its reverse. Composition and transitive closure fall straight out of Boolean matrix multiplication. That is the whole move. Choose the representation in which the property you are testing becomes the obvious, visible pattern. This section explains what a closure of a relation is. Add exactly what a property demands, nothing more. That is a closure. Given a relation, R, that fails to be reflexive, symmetric, or transitive, its closure with respect to that property is the smallest relation containing R that has the property. Smallest is what makes it unique, an infimum in the lattice of relations ordered by inclusion. The move is always the same free construction. Reflexive closure adjoins the diagonal. Symmetric closure adjoins the inverse pairs. Transitive closure adjoins every pair joined by a path. The reachability relation, R star, which is the union over all n of R to the nth power. Each of these answers the same two questions. What must I add to satisfy the property, and where does adding more to fix it? Stop. The answer is a least fixed point. You close when nothing new appears. This part explains equivalence relations and why three separate axioms turn out to be one structural act. The three axioms, reflexive, symmetric, and transitive, collapse to a single move. They are exactly the conditions under which a relation carves its set into disjoint blocks. An equivalence relation is a partition, seen relationally rather than set, theoretically. The correspondence between them is a bijection, not a resemblance. Each axiom governs one feature of the blocks. Reflexivity keeps every element inside its own block. Symmetry makes the word related, undirected. Transitivity forbids two blocks from touching without merging. So equal for present purposes, congruence modulo n, same cardinality, parallel lines, always resolves to one thing: it lands in the same class. Every notion of sameness, weaker than identity, wears this shape. To declare an equivalence is to quotient by what you agree to ignore. This section explains what makes a relation into an order. A relation becomes an order the moment three properties hold: reflexive, antisymmetric, transitive, nothing more. Strip the less than or equal to sign of everything numeric and this skeleton remains. So the same structure governs sets under inclusion, integers under divisibility, and tasks under divisibility. The generative surprise is what gets dropped: totality. Not every pair need be comparable. 2 and 3, neither divides the other. And this single omission is what lets order escape the number line and become a shape. Comparability is a privilege. Some pairs have, not a law. From those three axioms, plus the incomparable gap, everything downstream follows. The diagram of covers, the maximal and minimal, the lattice. Order is anti-symmetric reachability, not a ranking. This section explains what a graph is at the most structural level. A graph reifies a binary relation into an object you can walk. You forget what the vertices mean and keep only who touches whom. Every question the chapter poses is a property of that adjacency shape alone, invariant under renaming the nodes. Consider what those questions are. Are these two the same graph, which is isomorphism? Can you reach every vertex, which is connectivity? Can you traverse every adjacency, nodes, which is the Euler question, or visit every vertex exactly once, which is the Hamilton question? Can you draw it without crossings, which is the Hamilton question? Can you draw it without crossings, which is planarity? Can you color it with two colors? Each of these depends only on the shape of the adjacency, not on the identity of the nodes. One move generates the whole chapter. A graph is what its edges do, not what its vertices are. Grasp that, and each special type, simple, multi-directed, bipartite, collapses to a single constraint on the same underlying relation. This section explains what a graph is at its root. A graph is a binary relation you can draw. The vertices are the objects, and the edges are the pairs that stand in relation. That one move, turning is, related to into is, connected to, is the whole section. Everything after is bookkeeping over which permissions the relation grants. May a pair be joined twice, which gives a multigraph. May an object relate to itself, a loop, which gives a pseudograph. Does the relation carry direction, which gives a directed graph? So the model taxonomy is a decision rather than a list to memorize. You picked the coarsest graph type whose permissions match the phenomenon's structure. Acquaintance, competition, and influence networks all instantiate the same pattern. Any pairwise structure becomes a graph the instant you fix its vertices and its adjacency rule. This section explains how every term in the vocabulary of graphs is one relation seen from different angles. A graph is a single relation, incidence between vertices and edges, and every term here is a different reading of that one relation. Degree counts the edges at a vertex. Adjacency asks whether two vertices share one. The named families, the complete graphs, Kn, the cycles, the wheels, the hypercubes, Qn, the cycles, the wheels, the hypercubes, Qn, and the bipartite graphs, Knn, are just the incidence patterns regular enough to deserve names. The one theorem worth carrying is the handshaking relation. Summing all the degrees counts every edge exactly twice, so the total is twice the number of edges. Because of this, the number of odd degree vertices is always even. That is the generative move. Whenever a quantity attaches to edges through their endpoints, count it from both sides and read off the constraint. This section explains how graphs are represented as matrices and what graph isomorphism means underneath that representation. A graph is what survives, forgetting the vertex names. Write it as an adjacency matrix, and you have secretly chosen a labeling, a basis. So the same graph yields many matrices, one per ordering of the vertices. Two labelings describe one structure exactly when a permutation matrix P conjugates one adjacency matrix into the other, P times A times P inverse equals B. Isomorphism is conjugation by a relabeling. The graph itself is the orbit, and each matrix is a coordinate. Hence the working tool, invariance. The degree sequence, the triangle count, anything constant along the orbit. They can only refute a match, never confirm one, since sharing every cheap invariant still permits non-isomorphism. The general test stays a search over the permutation group. This section explains what connectivity means in a graph and where its structure really lives. Start with reachability. The statement that a path exists from U to V is reflexive, symmetric, and transitive, so it is an equivalence relation. That relation partitions the vertices into connected components. This is the same quotient move as Chapter 9.5's equivalence classes. Now read off a graph. A graph's coarse shape is just this partition. Asking whether the graph is connected asks whether the partition is trivial, that is, whether it has one block. Here is the generative turn. The structure lies not in the connections, but in where removing one piece breaks them. A cut vertex, or a cut edge, is a single element whose deletion splits one component into more. So connectivity measures reach, and the cut points measure fragility. Directed graphs merely split reach into strong connectivity, where a path runs both ways, versus weak connectivity, where you ignore direction. This section explains two graph questions that look like mirror images but behave completely differently. Walk a graph crossing every edge exactly once, and you have an Euler path. Visit every vertex exactly once, and you have a Hamilton path. The two sound symmetric, yet they diverge completely. Euler's question dissolves into a local count. A connected graph has such a closed walk if and only if every vertex has even degree, and an open one if and only if exactly two vertices have odd degree. Parity alone decides. One pass suffices, as Euler saw at Königsberg. Hamilton's question admits no local certificate. Deciding whether such a path exists is NP complete. The strongest results from Dirac and from Orr only by density guarantees, never a clean equivalence. The whole section lives in that asymmetry. Reindexing the word edge to the word vertex flips a linear time check into an intractable search. This section explains how a shortest path emerges without ever searching paths. You grow a set of vertices whose true distance you already know, and at each step you admit the one unknown vertex nearest to that set. The move that makes it work rests on non-negative weights. The closest frontier vertex can never be reached more cheaply by a detour through vertices still farther away, so its tentative distance is already final. Commit it, relax its neighbors, and repeat. That is Dijkstra. The primitive is greedy frontier, growth under a monotonicity guarantee, where a local minimum equals a global commitment. Predict the boundary yourself. Let one edge weight go negative, and the guarantee dissolves. The nearest vertex might yet be undercut, and greed no longer certifies finality. This section explains why planarity, whether a graph can be drawn without edges crossing, is really a question about counting rather than about drawings. Any crossing-free embedding obeys Euler's formula. Vertices minus edges plus regions equals 2. That quantity is invariant across every way you draw the same planar graph. So planarity stops being a property of a picture and becomes a conserved quantity. That invariant immediately caps the edges. The number of edges is at most 3 times the vertices, minus 6. From that cap, it follows that the complete graph on 5 vertices and the complete bipartite graph joining 2 sets of 3 cannot be planar. They have too many edges for their vertices. The whole chapter collapses to one move. A global geometric constraint reduces to a local arithmetic invariant. Kuratowski's theorem then closes it. Planarity fails only if one of exactly 2 forbidden shapes hides inside. This part explains graph coloring and the chromatic number. Color the vertices so that no edge joins 2 of the same color. The chromatic number of a graph. G is the fewest colors that suffice. That one constraint generates the whole subject. Adjacency means conflict. A color means a reusable resource, and the chromatic number counts the minimum resources that keep conflicting things apart. Rosen's three anchors are one pattern seen from three sides, matte regions where the four-color theorem says the chromatic number is at most 4 when the graph is planar, exam slots shared by a student, and radio frequencies that interfere. The compression is that a proper K coloring is a homomorphism into the complete graph on K vertices. So the question, is G K colorable, becomes the question, does G map into the complete graph on K vertices? The revealing boundary, a complete graph, forces the chromatic number to equal n. An edgeless graph forces it to 1. Everything real lives between. This section explains why a single constraint on a graph generates every application in the chapter. A tree is the graph stripped of redundancy to exactly the edge where connectivity still survives. Remove one more edge and it disconnects. Add one more and a cycle appears. That knife edge is the whole chapter. N vertices, n-1 edges, and between any two vertices, exactly one path. Everything Rosen builds after, in section 11.1, is a consequence of that uniqueness. Unique paths give unambiguous hierarchy, so trees store decisions, as in binary search trees and Huffman codes. They give addressing, as in prefix codes read with no delimiter. And they give ordered walks, the pre-ordered walks, the pre-ordered walks, the pre-order in order, and post-order traversals. Spanning trees, then run the move backward. Take a tangled graph and prune to the minimal skeleton that still connects everything, weighted minimally by greed through Prim and Kruskal. One constraint, generating every application. This section introduces trees and the single equivalence the whole chapter unfolds from. A tree is a connected graph with no cycles, but the generative statement is the equivalence hiding underneath. A graph is a tree exactly when every pair of vertices is joined by one and only one path. Connectivity guarantees at least one path. Acyclicity forbids a second. Redundancy and reachability are the two knobs, and a tree is the unique setting where you turn one to maximum and the other to minimum at the same time. From that single fact, everything else drops out. Hang the graph from any vertex and parents become unique. Count anything and you find exactly n-1 edges for n vertices. The whole chapter is the unfolding of exactly one path. This section explains why a tree is the right structure whenever a problem is a repeated choice. A tree earns its place exactly when a problem is a repeated choice. Make the possible answers, the leaves, make each internal node one branching decision, and the cost of resolving the problem becomes a root to leaf path length. That single move unifies the section's 3 anchors. The first anchor is binary search trees, where each comparison halves the remaining candidates. The second is decision trees, covering sorting, or the counterfeit coin puzzle, where n possible outcomes force a height of at least the ceiling of log base b of n, with b the number of results per test. The third is Huffman codes, where frequent symbols are bought shallow depth, to minimize the weighted path length. The surprise you carry forward is this. Log base b of the number of leaves is not an algorithm detail. It is an information floor, and no decision procedure beats it. This section explains what tree traversal is at the structural level. A tree carries only a partial order, ancestor before descendant, siblings incomparable. Traversal is the act of collapsing that into a total order, a single line you can read, print, or speak. The generative move is one recursive rule. Visit the subtrees and choose when to emit the root among them. Root first gives pre-order, root between gives in-order, root last gives post-order. The three kinds are one algorithm with a single free parameter, the position of the root. Structurally, it is a catamorphism, a fold consuming the tree in its own recursive shape. The universal address scheme, written 1.1.2 in Dewey Decimal style, is just pre-order written down. The numbering is the linearization. This section explains what a spanning tree is and why it sits at a critical point. A spanning tree is what a connected graph becomes when you strip it down to the edges that reach every vertex, no more and no fewer. Remove the edges lying on a circuit one at a time. Each removal kills a redundant path, but never disconnects the graph, because a circuit gave you two routes between its endpoints and you deleted only one. Stop when no circuit survives. What remains is exactly n-1 edges for n vertices, the critical point where one more cut would disconnect the graph and one more edge would close a loop. There is an equivalent way to build it. Grow outward from a root, adding only edges that reach an unseen vertex. Whether you go depth first or breadth first merely orders the same skeleton. The tree is connectivity held at minimum cost. Everything above it is slack. This section explains minimum spanning trees, and it comes from Rosen's Instructor's Resource Guide, a table of contents plus exercise solutions, so section 11.5 arrives as a heading with no expository body. The material is stable formal content, rendered from Canon. The problem is to connect every vertex at least cost. The cheapest connected subgraph is forced to be a tree, because any cycle carries a heaviest edge you can remove. The whole section rests on one improbable fact: pure greed reaches the global optimum. Two algorithms realize this. Kruskal sorts all edges and swallows the cheapest one that closes no cycle. Prim grows a single tree, always annexing the lightest edge, leaving it. Different orders, identical cost. Greed usually fails, because the locally best step strands you. But a spanning tree has matroid structure, so the safe edge choice is never regretted. That exception is the concept. Recognize the terrain where looking one step ahead is looking all the way ahead. This section explains Boolean algebra as one algebra shared by logic, sets, and circuits. Two values, three operations, one discovery. The algebra of the set containing 0 and 1 under join, meet, and complement is the same object whether its elements name truth values, subsets, or the open and closed state of a switch. That is what the chapter carries. Propositional logic, set operations, and circuit design collapse into one axiom set: commutativity, distributivity, and the complement laws. Prove De Morgan once, and it holds in all three. Because every Boolean function admits a canonical sum of products, form, circuit synthesis becomes algebra. Write the normal form, then simplify. Minimization, the sections that follow, exists only because that canonical form is correct, yet rarely the smallest. This section lays out the skeleton that Boolean algebra imposes on every switching circuit, every propositional formula, and every finite algebra of sets. Two values, three operations, and all of those structures collapse onto a single shared form. Boolean algebra is arithmetic on the set containing just 0 and 1. The complement flips a value. The Boolean sum keeps the larger of two values, which is the operation logic calls OR. The product keeps the smaller, which is the operation logic calls AND. A Boolean function of degree n is any map from n. Boolean inputs to a single Boolean output, nothing beyond a truth table. So there are exactly 2 to the power of 2 to the n of them. The chapter opens on a thesis of substrate indifference. Whatever you prove about logical and, or, and not transfers unchanged to intersection, union, and complement on sets and to logic gates in silicon. Complementation is what gives the order its teeth. It turns a mere ranking into a distributive, complemented lattice. This part shows how a Boolean function's own truth table hands you its formula. A Boolean function is completely pinned down by its truth table, so the table itself gives you a construction. Read off every input row where the function outputs a 1, write the exact and combination of variables that selects that single row and or those pieces together. Each such piece is a minterm, true at one row and nowhere else. Every function on any number of variables is therefore a finite or of minterms, a sum of products. The deeper move is that, and, or, and not suffice to build anything, and you can shrink that kit further, since not, and alone, regenerates all 3. Expressiveness is constructed from the table upward. This section explains what a logic gate is and how Boolean algebra becomes physical hardware. A logic gate is a Boolean operator given a body. The inverter negates, the AND gate multiplies, the OR gate adds, and wiring them in cascade realizes any Boolean function as a physical object. Here is the pattern that carries over. A circuit is the composition tree of an expression, so the sum of products formed from the previous section drop straight onto hardware as 2 layers, one bank of AND gates feeding a single OR gate. Boolean algebra and combinational circuitry are one structure, wearing 2 substrates, symbols on paper and voltage on silicon. Reading a circuit is just evaluating the expression it draws. One boundary marks the limit. Gates hold no state, so this maps functions only, never memory. This section is about shrinking a circuit to its smallest correct form. Every truth table hands you one honest expression, an or of products, one product per true row. That form is correct and wasteful. The whole trick rests on a single adjacency law. 2 product terms that differ in exactly one variable collapse into one term with that variable deleted, because a value and its complement together cover both cases. So minimization becomes a covering game on the Boolean cube. Tile the true rows with the fewest, largest blocks whose corners are all neighbors. A Karnaugh map makes those neighbors visible. Quine and McCluskey make the same search mechanical when the variables outrun sight. This section explains what the whole chapter is for. Computation is modeled by machines, and a machine is defined by exactly one thing, which strings it accepts. A language is a set of strings. A grammar generates them, and a machine recognizes them. These 2 faces, generation and recognition, turn out to be dual. The quiet surprise is that a machine's memory structure alone fixes its power. Finite state machines, carrying no scratch memory, recognize precisely the regular languages. Give a machine an unbounded tape, and you reach the Turing machine, the outer limit of what anything can compute. To compute, in this chapter, is to recognize. This section explains what a grammar is and why it can generate an infinite language. A grammar is a finite machine for growing strings. You begin with one start symbol, then repeatedly replace fragments according to a fixed set of rewrite rules, and every string you can reach this way forms the language. The surprise is the asymmetry. A handful of rules generates a set that is often infinite, because a rule can reapply without end. A language is therefore the closure of the start symbol under rewriting. Grammatical means reachable. This is the same generative move as an inductive definition. Name the seed, name the steps, and the object simply is whatever those steps produce. This section explains the primitive behind a machine that reacts without remembering. A finite state machine with output, the Mealy machine, folds its entire past into one of finitely many states. Each input does two things at once. It emits an output, and it moves the machine to a next state, both fixed by the current state together with that single input. The state is a sufficient statistic of the history. Whatever the past could matter for is already carried in which state you occupy, so the machine never rereads what came before. Bounded memory is what buys unbounded input, and the transition table, mapping each state and input to an output and a next state, is the entire machine. This section explains what a finite state machine becomes once you strip away its output. Take a machine that reads symbols one at a time and moves between states as it reads. Remove the output and its entire behavior collapses to a single question. Does the string leave it resting in an accepting state or not? The machine stops transducing and starts deciding. Every possible string is sorted into two bins, accepted or rejected, so the machine now denotes a set of strings, a language. That is the whole move. The output did not disappear. It compressed down to one bit, membership. The same transition structure that once emitted symbols now draws a boundary through the space of all inputs. This section explains how a finite state machine recognizes a language and the single theorem that makes finite memory and a small algebra of operations the same thing. A finite state machine is a classifier over strings. Feed it a word, let it walk from state to state on each symbol, and accept if the walk ends in a final state. The language it recognizes is just the extension of that accept test, the set of all strings that land inside. The chapter's single thesis is Kleen's theorem. This set is regular, buildable from single symbols by union, concatenation, and the Kleen star, if and only if some finite state machine recognizes it. Finite memory and this closure algebra are the same object, seen twice. And non-determinism. Guessing branches in parallel buys no new languages. The deterministic and non-deterministic recognizers denote exactly the same regular sets. This section explains what a Turing machine is and why it sits at the summit of the machines this chapter has built up. A finite state machine remembers only which of finitely many states it occupies. A Turing machine adds exactly one thing, an unbounded tape it can both read and rewrite, and that single addition is the entire leap. Bounded memory recognizes only regular patterns. Unbounded rewritable memory computes everything that can be computed at all. So this concept sits at the top of the chapter's ladder of automata, the machine every weaker one merely approximates. Its point is definitional rather than practical. The Turing machine is the reference model against which the word algorithm acquires a precise meaning, and against which certain problems can be shown to admit no algorithm whatsoever.